Questions about anything from last time or anything? Well, I almost got myself ready to prove the famous maximum principle, the maximum modulus theorem for analytic functions. And a couple lemmas. I need one more little lemma that's the key to deducing the maximum principle. And it's based on a very simple calculus fact that if you have a continuous function, real valued, on a closed interval that's greater than or equal to 0 for all t, then if that integral, if the area under the curve is 0, then of course the function has to be identically 0. And so, example, let's say the integral from 0 to 2 pi of sine of t dt is equal to 0, but of course that doesn't imply that sine is 0. Because sine is not a positive function on it in that interval. It has as much area above the graph as below the graph. But if I knew in advance that the function was greater than or equal to 0, then of course that area being 0 means that the h never goes anywhere. So the proof is the proof of the lemma is pretty straightforward. So here's my continuous function from a to b. Let's suppose it's not identically 0. Then it would have a bump somewhere. Let me see, I'll make it be 0 for a while and then have a bump. 0, bump. Okay, let's suppose it's, we could make that be the max, what the heck. So this is if h does not, h, let's call this spot here t naught. H of t naught is greater than 0. So let's suppose that. Well, if h of t naught is greater than 0, we have continuity. So let's let epsilon be equal to h of t naught over 2. Then, because of continuity, there exists a delta such that h of t minus h of t naught is less than that epsilon when t minus t naught is less than delta. Okay, and think about what that means here. Here's my epsilon. Wait a minute, no, my epsilon is t. That's my h of t naught, and my epsilon is halfway. Okay, so if h of t minus h of t naught is less than that epsilon, then you'll notice that this little box here, this is t naught minus epsilon, and that's t naught plus epsilon. That little box is contained. So this would be t naught plus epsilon. This would be t naught minus epsilon. What we see here is that the box of size, of area, epsilon times 2 delta, epsilon times 2 delta, is under the curve. So we get the contradiction. So the integral from a to b of h of t dt is greater than epsilon 2 delta And of course, that's greater than 0. And that's a contradiction. So my assumption that there's a spot where it's not 0 is wrong. Questions about that? It's a very elementary lemma. But it gives me a... I'll do this lemma upside down. So this is the upside down version. Of that lemma. Let's suppose...
Why is the box not around the point that you're, like, around the epsilon?
What?
Why is the box not around the, like, epsilon?
Let's see, the t is going from... the t is where... See, the h function is there. It's within h of t. This little thing right here is h of t naught. So if it's within a distance, h of t is within a distance of epsilon, of that h, that's h of t naught over 2, it would be above that orange box. So that orange box is underneath. You agree that the h of t here, in this section right here,
So the orange box is further than epsilon from...
h would have to be above that orange box. So that orange box is under the curve.
Okay.
And the upside down version is, suppose I have an h that's still real valued, maps AB into the real line, and let's make it 0 is less than or equal to h of t is less than or equal to some m. Then if that integral is as big as it can possibly be, so if I integrate that function from a to b, and if I actually get the biggest it can possibly be, then which is m times b minus a, then h of t is identically equal to that max. Of course, the proof is exactly, the proof would be apply the lemma, replace h by m minus h in the first version. Or to get a picture feeling for it, so here's the picture. We've got this function h from a to b. It's less than or equal to m. Let me make a dotted line going across m here. If it ever dipped below m, the bump this time would be underneath m. Then the upside down version would allow me to put a little orange rectangle in here like I did before. And that would make that integral strictly less than that max possible. The area of this rectangle is m times b minus a. So it can't dip below when you do that proof upside down. Let's first do the maximum modulus on the disk. Maximum modulus principle. Let's do the first case. The disk of radius r about a. So I've got a, I'm sorry, I want, I've got this disk, and let's suppose f is analytic on a bigger disk. F is analytic on a bigger disk. with r bigger than a. I mean r bigger than little r, capital R. Let's let M be the maximum of the modulus of f of z such that we're in the closed disk. Z minus a is less than or equal to r. And the fact is, if f of a, that's the center, is equal to m, then f is constant. On that disk. Well, the proof is just going to be, let's see, f of a, remember, satisfies the averaging property. So that's the integral from 0 to 2 pi of f of a plus r e to the I t dt. Okay, that's the averaging property. So now next let me take the modulus of that. And so I get the modulus of f of a, which by the way is, I'm assuming that's m. That would be less than or equal to 1 over 2 pi times the integral from 0 to 2 pi of the modulus. This is the basic estimate for integrals. The number one, the easy one in the simpler case of a complex function of a real variable. And this is the h of t in my calculus lemma. This h of t is between 0 and the m, because m was the max. And so this is less than or equal to, let's see, I got a 1 over 2 pi. So it's less than or equal to 1 over 2 pi times m times the length of the interval, which is 2 pi. 2 pi's cancel. And we see that that integral is the max. We see that the integral from 0 to 2 pi of h of t dt equals the max times 2 pi minus 0. So h of t is identically equal to m on the circle. Okay, so what do we conclude here? We conclude that f of a plus r e to the it is identically equal to m as t goes from 0 to 2 pi. And now when you think about, okay, that's interesting, it has to be constant on the outer circle, there was nothing stopping us from using a smaller radius. So the aha here is the same holds for any radius. Any radius, rho, with 0 less than rho less than r, by exactly the same reasoning. So we conclude that modulus of f is identically equal to m on the whole circle. And now, remember the lemma from the last time was if the modulus is constant of an analytic function, the function is constant. So our lemma from last time implies that f is identically equal to constant. Okay, so that's a maximum mod. If the maximum occurs inside, then it's constant. Okay, now I'm going to prove the maximum modulus theorem. Remember what it was. It's let's suppose omega is a bounded domain. That's important. And we need f to be continuous up to the boundary. And f is a continuous complex valued function on the closure. Which we write the closure of omega as that. Which is analytic inside. Inside omega. Okay, omega is its own inside since it's open. So instead of saying inside, I should say on. Of course, because it's continuous, the max exists. The max is attained on that closed set. Then m equal the max of the modulus of f of z when z is in this closed and bounded set is assumed at some point on the boundary. I'll call it z naught in the boundary. Note, this is a closed and bounded set, so the maximum is attained. F continuous on, or say the modulus of f is continuous on the closure. So the max is assumed someplace. Someplace in the omega closure. I'm going to say that I'm going to prove that it's assumed on the boundary. It might be assumed other places, but it's definitely going to be assumed at some point in the boundary. Okay, the proof is going to be interesting. It's going to be a case where I have to do something topological. And it takes a while to get the hang of topology arguments. So let's say, let's do the case. So the max is assumed. Say the max is assumed point z naught, some point in omega closure. So that means the modulus of f of z naught is the max. Well, the case when z naught is in the boundary, we're done. Done. I mean, sorry, z naught's in the boundary. I'll call the boundary b of omega. Topology books write, instead of writing b of omega, they write d of omega. B, that's the boundary of omega in topology notation. But in complex analysis, d stands for something, namely the d operator. It's like the total differential df, but it's in the complex case. So it's a curly d, and it's like it's related to Cauchy-Riemann equations. So that curly d is a reserved symbol in the in complex analysis. So I call the boundary b omega. I like it better. That's the boundary. Of omega. Well, then we're done. So that's a dumb case. Now let's do the next case. Case z naught is in omega. Well, then z naught, since omega is open, that implies there would be a disk of radius r of a closure contained in omega. Okay. And that means now that thing I did in the case of the disk above, disk case above shows that F is identically equal to M on that disk. And now here's the topology argument. Okay, so here's my domain. Big blob, looks like a potato. But it might have a hole. Okay. Here's my z naught. Let me move my hole. Okay, here's my z naught. Here's my disk of radius r. And let's pick any old other point around here. How about a z over here? If I take a curve that starts at z naught and goes to z, let's call that gamma. And let's parameterize gamma by z of t as t goes from little a to little b. Interesting thing, notice that there'll be an interval about a where that function, let's consider, so let's note f of z of t is identically equal to m for t on an interval for t in a to a plus something. For some delta bigger than 0. Because it was on that purple circle, it's equal to, inside that purple circle, it's identical to m. And by continuity, there'd be a little delta there, so that would be the case. And so in topology, we're using connectivity here. And so imagine, now you put, I'm going to erase this in a second, but imagine you go here now. It assumes the value m there, and so I would get a circle, a bigger circle, and I can move that out farther, and I could keep doing that. It's like taking a cloth and extending it blob by blob. And the question is, do you get to the end of the curve when you do that? And when you think about how in the heck you might prove that, you'll come up with this idea probably. Let's let tau equal the maximum t. Let's see, the maximum. I got a t. Oh blast! So let's see that. Let's let tau sub m be the maximum tau, such that f of z of t is identically equal to m for a less than or equal to t less than tau. Let's make it less than or equal to tau. Well, I claim that max has to be b. I can get all the way there, all the way to b. Notice that tau is bigger than a. Tau max is bigger than a, obviously, because of that fact above. The question is, how big is it? And I claim it goes all the way to b. And here's why. If it was less than b, so we know tau m is bigger than a. If tau max is less than b, well then you've got this, my green curve here would start at z naught and go to z, and it would be b on a whole bunch. This would be z of tau max, right there. It wouldn't get all the way to z. But if I take that purple disk now and stick it around here, I would see that I could extend it. So let's see, f of z of tau max is equal to m, and I would see that I could extend the distance beyond the max. So I would get a little disk like this. Who knows how big it would be? It maybe be smallish. Okay, this little thing right here is z of tau max. And then I would get constantly equal to m on this shaded thing for a disk. And I see that tau max is not the max. So I would get F equal to M on a disk about Z of tau M. And so tau M is not the max. And that's a contradiction. So that means I get all, that's it. That picture is valid if I don't get all the way to the end. And so I have to get all the way to the end. That's the contradiction. That's how you should. So that's a typical connectivity argument. And so what I've shown you is that we conclude F is identically equal to M on omega. And so by continuity, it's constantly equal to M on the closure too. So the max is attained on the boundary. Done. I told you about the fancier version. Last time. If F assumes a local max, at a point Z naught in omega, and in this case omega doesn't have to be bounded. Then F is constant on omega. And the proof is going to involve an ingredient we don't have yet, and that's why I'm not doing it today. So the proof, if it had a local max, then that means that you'd get a disk, dr about Z naught, contained in omega, make it a closed one, where the modulus of f of Z naught is the max. That's what it means to be a local max. Then our fact we showed is that f would be constant on that disk. Then from above, the above work, we know f is identically equal to constant on at least that disk. And to finish it off, a big fact for later, soon in fact, big fact coming soon. If a analytic function vanishes on a little disk, it has to vanish on the whole domain. That's a fact. And so if it's constant on a little disk, it has to be constant on the whole domain. Just think about f minus the constant. So the big fact is if f is identically 0 on a disk, an open set, in the domain omega, then f is identically 0 on omega. Okay, so if it was constant on that little disk, then, of course, it would have to be constant on the whole thing. So I would apply this big fact to f of z minus c if f is identically equal to c on the disk of radius r about z naught contained in domain omega. Okay, so the punchline for that fact would come later, but at least I'll state that big fact now. You might ask, any questions so far? You might ask, is there a minimum principle? If the modulus is at minimum someplace, does it mean the function is constant? Any think of a function, a really simple function. No, there isn't. If I take f of z equals z squared, for example, has a minimum modulus at 0. But it's not constant on the complex plane. On C, or the unit disk, or any domain that contains 0. But if f is a non-vanishing analytic function, then you can apply the maximum modulus theorem. But if f is a non-vanishing analytic function, analytic function on a domain omega, there is a minimum principle. And it's trivial to see why. There is a minimum modulus theorem. And the proof would be when f is non-vanishing, you apply the maximum modulus principle to 1 over f. So that would be all there is to that. Oh, okay. Okay, we've seen that the averaging property was the key in the maximum principle. And so you've seen the averaging property was the key to my showing the maximum principle. Well, I claim that harmonic functions satisfy the averaging property. And so, of course, there's going to be a maximum modulus, a maximum principle for harmonic functions. Okay, this is an easy thing to see, because let's suppose U is harmonic. Is harmonic on the bigger disk, on dr of A. Well, we get a harmonic conjugate for that. We know how to do that. Let's get a harmonic conjugate. V for U on that disk. So F equals U plus IV is analytic. And we have an averaging property for F. So if R is less than, if 0 is less than little r is less than capital R, we know analytic functions satisfy the averaging property. So F of A, that would be U of A plus IV of A is equal to the average. 1 over 2 pi integral from 0 to 2 pi of F of A plus RE to the IT dt. And that's that integral is defined as the real part plus the imaginary part. So the real part would be U of A plus RE to the IT dt plus I times 1 over 2 pi, same thing for the V function. And now when you see the equate the real parts, this is the real part on the left. This is the real part on the right. So we equate the real parts. The real parts, and then you get the averaging property. There's the averaging property for U. Check. And so I'm not going to repeat them, but I can do a straightforward repeat of the analytic stuff and get a maximum principle for harmonic functions. So it's straightforward. In fact, it's even easier because I don't have to deal with the modulus. So it's straightforward to repeat the arguments above. For analytic functions. To get a maximum principle for harmonic functions. And there's that harmonic functions are even easier because then you can get a minimum principle just by taking minus U in place of plus U. So we get a minimum principle too. It's not by applying the maximum principle to minus u. Okay. Well, I don't want to bore you to death just by repeating all that stuff because it works great. I should also point out there's kind of a neat trick. Here's a nice trick. If I take a harmonic conjugate, I can have an f equals u plus iv. And so the modulus of e to the f is, let's see, that would be the modulus of e to the u times e to the iv. That would be e to the u times the modulus of e to the iv. The modulus of e to the iv is 1, because it's not iv, that's a point on the iv would be going around. E to the I something is a point on the unit circle, or cosine v squared plus sine v squared square root. So that thing's equal to 1, and this thing's equal to e to the u. And so that modulus is e to the u. And if u had a max, then that e to the f would have a max. So I could deduce the maximum principle for harmonic functions by reducing it to the analytic version. So if I said that u has a local max, at z naught implies the modulus of e to the f has a local max. At z naught. And that would imply that e to the f is constant. And let's see, that implies that u is constant. The answer is yes, of course, because, let's see, let me think. If I'm looking at that stuff I wrote above, I have that e to the f modulus is e to the u. And that would be a constant. E to the f is constant, so the modulus of e to the f, it would be constant. Let's say constant c. Let's see, e to the f is never 0, so that constant c would be unequal to 0. And then we see, the answer here is yes. U would be identically equal to the natural log of c. So check. So you can prove a maximum principle for harmonic functions when you know the analytic version. I'm sweeping something under the rug here. I need to know that I have a harmonic conjugate to do this. But if I can do it on a disk, then that big fact I mentioned, I can use that big fact. If I get it constant on a little disk, it's constant on the whole region. And I could use that later. So I'm not going to worry about the details here today. Think about doing this on a disk where you know you have a harmonic conjugate. It would work great on a disk.